So now let's jump into the mathematics of classifying um, data, let's say, into two or more pieces. First, we will look at classification that divides data into two pieces, or divides, I guess, the world into two pieces. This would be called binary classification. So we'll do that first for a few lectures, and then we will generalize that to what's called multi-class classification, where we look at classification into different classes or multiple categories, maybe tens of thousands of categories. Okay, so let's first look at an example that's now motivated by mechanics. Imagine you have a metal piece, maybe a sample that you would use in a tension test of a material, right? And let's say you have 10,000 versions of this piece. They're all approximately identical. And now we draw a sample from this collection, and then you perform the following kind of a tension test. It's kind of a weird tension test, maybe not quite traditional. But let's go with this. I'm just trying to provide a motivating example for the kinds of data that we will have. Okay, let's say we load the piece up to some randomly chosen stress level sigma, right? So you let's say you impose a stress level sigma on the material using some tension testing apparatus. Okay, it's a bit unconventional, especially because of the randomly chosen stress level. And then you see whether the metal piece breaks or not. In other words, whether there is failure or not. Okay, and then we keep doing this for all the samples in this collection of 10,000 samples, okay, of this metal piece. So we have essentially 10,000 data points, and we say if the piece of metal fails, you say the output of that experiment is 1, and then if it's not failed, the output of that experiment is 0. Okay, the input, quote unquote, of this experiment, of this data set, is the applied stress sigma. Very crudely, let's say it's uniaxial stress, just to simplify conceptually this data set. Okay, so what would be the kind of data that we might get? Okay, this might be a kind of data that you might get where you plot sigma, the stress applied, on the x-axis, and then this result, this discrete output, whether the sample failed or not, as the output, which is 0 or 1. Okay, so you can imagine, for instance, if the materials are somehow perfectly machined and they're all perfectly uniform, and there is somehow no stochasticity in its response, then you might expect the following kind of behavior, where below a particular stress level, the failed or not output is basically 0. In other words, the material does not fail, and then above a particular stress level, the material basically fails. Okay, you can express this kind of data in the following manner, where you say the probability. So now we are taking a probabilistic sort of framework. The probability of failure equals 1 when the stress level exceeds some threshold called sigma failure, and the probability of failure is 0 when the stress level does not exceed this threshold called sigma failure, right? So this kind of data can be expressed in this sort of simple manner, where this dividing line is the sigma failure threshold level. Okay, so you could have data that looks like this. You might also have data that looks like this, where there is a kind of overlap between the regions where the material fails versus the material does not fail. Okay, where you can say, perhaps it so happens, for really low stress levels, the material does not fail. For really high stress levels, the material fails. And then for intermediate stress levels, maybe the material sometimes fails, or some samples fail, and then for some other samples, even though you're roughly in the same overall external forces applied, let's say, or the conditions applied in the experiment, sometimes it fails and sometimes it doesn't. Okay, so I've sort of noted these thresholds to be sigma 1 and sigma 2, where the probability of failure is 1 for sigma greater than sigma 2, the stress greater than sigma 2. The probability of failure equals 0 for sigma less than, or equals 1 for sigma greater than sigma 2, I should have said here. Okay, sigma 2. And then probability of failure equals 0 where sigma less than sigma 1. In other words, less than here. There's a typo here. Exchange these two things. And then the probability is between 0 and 1 when the stress level is between sigma 1 and sigma 2. Okay, in this region. Okay, that's a plausible scenario, and that could arise because of imperfections in the sample, all the samples not being perfectly identical, maybe some randomness in the application of in the control of this input, etc. Right? You can imagine all those possibilities. Okay, so that's you can imagine that kind of data. Now, how would we encapsulate data that looks like this? One way to encapsulate it is actually try to fit a function, right? So if you wanted to summarize this data, all you need is this one number, namely sigma failure, where you say p failure equals 1 when sigma is greater than sigma failure, and 0 if otherwise. Here, for data that looks like this, maybe you want to summarize it by fitting a function of this form, maybe, where you say the failure probability is 0 when you are less than sigma 1, the failure probability is 1 if the sigma is greater than sigma 2, and then maybe the failure probability increases linearly if you are between these two stress levels. Okay. Okay, so that's the difference between these two kinds of data sets, where this linear thing has been replaced by a sudden jump if all the materials break at a exact same stress level. Okay. Now, it turns out that it is conventional to try to approximate data of this flavor, not necessarily this failure data, but data that have this discrete output flavor using what is called a logistic curve or a sigmoidal curve. What does this curve look like? It looks like this, right? So where it's actually, rather than having these three pieces, it is one continuous arbitrarily differentiable function which goes to 0 at minus infinity actually, and goes to 1 at plus infinity. So of course minus infinity doesn't make sense. Maybe other things will happen if you apply a compressive stress instead of a tensile stress, for instance. Nevertheless, let's say we want to approximate this kind of data with this continuous smooth function, okay, where the raw data itself is binary. In other words, the raw data takes only values 0 or 1, but then you're trying to approximate the probability of, in this case, the sample failing using this sigmoidal curve that smoothly goes from 0 to 1. And there is a transition region. You can make the transition region steep, thereby trying to approximate this, or if the transition region is gradual, you might be able to approximate something like this. Okay. Okay, so by the way, if you just wanted to estimate the probability, how would you get it from data that looks like this? What you can do is actually bin. We'll talk about this maybe in a MATLAB program. You can actually bin, in other words, divide the stress levels into little pieces. So imagine stress levels from here to here, and look at whether all the samples, what fraction of the samples for those stress levels failed or not. That's basically probability of failure, right? So if you consider samples that have experienced stresses in this range and look at what fraction failed, that's going to be the probability of failure. So you essentially divide the whole range of stresses applied into little bins, BINS, and see what fraction failed in each bin, and that will give you a curve like this, right? So if you take a bin here, of course all of them will have failed, and that'll give you 1. And in a bin like from here to here, maybe 80% will fail, and that'll give you 0.8 here, right? So that's how you would construct a curve like this. Okay, so you can construct a probability curve like this based on data, raw data, that always has either failed or not failed, right? So you convert discrete data into continuous data like this, and then maybe you can try to approximate this data with what's called a sigmoidal curve. It's also called a logistic curve. It so happens that some of these words have weird historical origins. Sigmoid, it's called sigmoid because it's an S-shaped curve. S is sigma in one of these old languages. Now it's called logistic because it has to do with something called the logistic equation, which is used in population growth and in fact epidemiology. Maybe you've heard this equation used in popular scientific accounts of the growth of COVID-19, for instance. In any case, yeah. So it's got its origins in a completely different field. This term, at least. Approximating population growth or growth of an epidemic using differential equations is where this term comes from, I believe. In any case, it's also called a sigmoid curve, like I said. And trying to fit curves like this to data that looks like this is basically what's called logistic regression, because you're fitting a logistic curve. Okay. Okay. So we'll stop there for this video and then pick up the mathematical details in the next video.